So let's continue with examples of graphs, and then as we go through, we'll fold in more terminology. So here I want to kind of draw 3 examples of graphs and introduce a concept that's really important. So alright, so you're right if you think this is supposed to look like a cube. That's exactly why I'm drawing it the way I'm drawing it. However, I do want you to think about it as a graph that's been drawn on a 2-dimensional surface. Okay, so try to keep both thoughts in your mind. It suggests that if you were to put this in 3D, you could make this into a nice even cube. That's certainly true. But also think about, like, if it was a frame of a cube and then you do its shadow, this is the shadow of that. And it's still a graph, right? There's points and there's edges connecting those points together. Okay, so let's call this G. Okay, let's call this graph G. We're probably going to go back in here and create vertex labels here in a second, but let's do another one, H. Okay, and hopefully you're starting to have some thoughts about how G and H might relate. Let me do one more. I'll call it I. Well, it's a weird name for a graph, but that just goes in the alphabet. This is supposed to be an octagon. Alright, so take a minute, look at this, start thinking about what might these graphs have in common. And in fact, in common might be actually too weak of a way of saying this. When it comes to the graphs, hopefully you're starting to realize that they do seem to look a lot alike in many respects, okay? But they do have different features related to how I drew them, right? So this one has some edge crossings, this one has no edge crossings, this one has a bunch of edge crossings. Sort of the arrangement of the vertices is a little bit different in each one. But there is a concept that's incredibly important here, and that is all 3 of these graphs are isomorphic to one another. So in fact, there's 3 statements I can make. So G and H are isomorphic. H and I are isomorphic. And this is the new word here, isomorphic. And it turns out also G and I are isomorphic. Okay. It is true that the concept of isomorphism is transitive. So since G is isomorphic to H and H is isomorphic to I, then G is isomorphic to I. Alright, so what is this concept of isomorphism? It's very much what you might think it is. Alright, but the task to do this is you, I'm going to make a definition here. I also want to have spots to do the work. Sorry, I want to do it here. Let's do it on the bottom left. Alright, so 2 graphs, G1 and G2, are isomorphic if there is a 1-to-1 mapping of the vertices that preserves adjacency. Okay, so two vertices, if they get mapped to other vertices, if they were adjacent in one, they better be adjacent in the other. Or if they were non-adjacent in one, they better not be adjacent to each other in the other either. Right, so you can just check this pairwise. And in fact, that's not actually a very expensive thing to check, right, in terms of computational power. Right, we've done some counting stuff first. You actually know, right? You would have to know how many pairs would I check. Here I have 8 vertices, so I have to do 8 choose 2 checks, right? There's 8 choose 2 pairs. Alright, so this is how you build an isomorphism. And if you can build one of these things, the mapping is called an isomorphism. If you can build one of these, then they are isomorphic. So let me show you this conceptually the easiest way of doing this. They usually don't come to you this way though, so keep in mind this is not always going to look this way. These are unlabeled graphs, and so that is sort of a luxury. I'm going to start off by labeling these lowercase letters this time. And then I'm going to do, so A, B, C, D, if you think, well, to me this looks like the front. I'm not sure if it looks like the front or the back to you. It actually just depends on which way your mind pops it out. And we go E, F, G, and H. And I'm using lowercase letters because I've used uppercase letters for my graph names. So I'm just going to switch to lowercase so you can see that way that the G's and the H's don't get confused with one another, hopefully. Alright, so to make this mapping, believe it or not, there's not a lot to do, especially if it's unlabeled, but even if it is labeled, you just have to use a labeling procedure, which is a mapping. A mapping is a labeling procedure to label this. So there's actually a bunch of isomorphisms that would work, but I'm going to choose one to me that looks the simplest. So if I label this one A, B, C, and D, I should be able to check a few things. So first of all, are A and B adjacent? Yes, they are here. Yes, they are here. Okay, so that checks out. A and C are not adjacent here, and they are not adjacent here either. Right? You can check this with the other pairs too. So you would think, okay, so far so good. Okay, you can say, okay, what else is D adjacent to besides A and C? Well, D is adjacent to A and C. It's also adjacent to E. So this kind of has to be E at this point if we have any chance of this working out. How about E? E is adjacent to D, but what else? Well, E is adjacent to H and F. Now I can't put H here, right? Because H is adjacent to A, not C. So H needs to be up here. And same thing so far. So you can kind of play with this, and then the last one has to be, sorry, it's Friday and I'm tired. This has to be G. Yep, okay. Alright, now I'm satisfied with this. So if I was asked to show that G and H are isomorphic, and if I had no labels, I would do this. This would be my job here. Okay, and I'll show you another way that this could be done if you're given labels. Alright, this is actually enough. This shows that one-to-one mapping. I did not label 2 vertices C, right? That would be a 1-to-2 mapping, or 2-to-1 mapping, depending which way you go. They all have unique labels, just like this one did. So you would double check to make sure, okay, is E and F adjacent to the other one? They are, right? And so you could do this pairwise. So it's sort of incumbent on the reader to call you out if it's not an isomorphism, but it's actually not that hard to find. So occasionally from my end, when I'm checking your work, I can usually tell if you nailed it, or if you've missed something, I can usually find a glitch in your isomorphism. So anyway, so G and H are isomorphic because I completed that task. All right, I'm going to do the same thing here. I'm going to do A, B, C, and D. Okay. Now why am I doing that? Well, I'm considering this sort of vertical rectangle as a version of this little square here. Okay. And a few comments to make about this in a second, but do that. Okay, A is adjacent to B and D. It's also got to be adjacent to H, so this has to be H. How about G? G is adjacent to B, so I bet this is okay. F and E. So double check, make sure this makes sense. Okay. So these are 3 versions of the same graph. Okay. And they are isomorphic to one another. So, if this was relatively easy, or not too extremely difficult, I'd like for you to keep in mind that this is actually an incredibly powerful part of human psychology, or the human brain, or ability to do this. This is an advantage that the human mind sort of has typically over a computer. A computer doesn't really see these in the same way you would. Really, all they see is sort of an adjacency list. That's it. These pictures actually are sort of something we can leverage in our own mind. And if you want to practice this, you can think about shifting and moving one graph into the other. You can actually almost see, if you practice, a continuous deformation of one into the other. Right? This one, all you have to do is take the A and the B and the CD and stretch it up. And this one just kind of shrink and stretch it down. Right? So with some practice, you can see your mind can actually be quite good at this. And it's a skill a computer generally does not have. Now that's not to be said, maybe it's something trainable, but keep in mind there are elements of where my tip to you is going to be, you kind of have to practice recognizing this particular feature or pattern. It's not algorithmic all the time. So to do some of these examples, they're really just examples. To see things, you have to practice seeing pictures. All right, so what else is there to say here? Let's do one, because I think it'll fit where there's labels involved. So let's do one more example of isomorphism. It's much smaller, but a chance to see how the book is going to ask you to do isomorphism problems. So I want to show two, this time I'll use G1 and G2. Bring back a graph I had last time. So I'm going to use numbers for those vertex labels, and for G2, I'm going to use letters. This graph is an extremely common inspiration for many logos. Turns out these two graphs are isomorphic. To show they're isomorphic, I need to find an isomorphism. I'll just do it in a different color to kind of make it stand out. It turns out this is a problem where you actually can't miss. Pretty much anything you start with, you can kind of follow through. But so let me pick something that's not totally on the nose. So let me take the vertex B and map it to 1. I can use an equality sign. I can use like an arrow, right, or something like that. Anything that connects or links B to 1 will be fine. Whatever notation you like. Right, so this is good. This is good. You can use an arrow one way or the other. All that's fine. I'll use equality. All right, then A. Let's see. So I'm not going to be too worried. I'm just going to see if things work out. I'm see a 1 is adjacent to, well, actually all the things. So let's let A be 2. I said 2 and I wrote A. 2. How about C? C is adjacent to A and B. It's also adjacent to D2. So what's adjacent to 1 and 2? 4 and 3. So let me just choose 4 for the fun of it. Okay. And then D would have to be 3 if this is going to work at all. Sorry, that's my brain trying to make a 3 backwards for some reason. All right. So let's double check, make sure this is isomorphism. And this one you can actually check pretty quickly because there's not a lot to check. Are A and B adjacent? Yes. Are 1 and 2 adjacent? Yes. How about B and C? B and C are adjacent. How about 1 and 4? Yes. How about B and D? B and D are adjacent. How about 1 and 3? Yes, 1 and 3 are adjacent, right? And you can do the last few. A and C? Yes. 2 and 4? Yes. A and D? Yes. 2 and 3? Yes. C and D? C and D are adjacent. 4 and 3? They are adjacent. Okay, and that's it. That's all the possible pairs you could possibly have, right? So 4 choose 2, so that's 6 pairs to double check. Okay, so turns out actually you could do this however you like, and that's because these graphs are what you'd call complete. Okay, they're both actually in a class of graphs called complete graphs. In fact, this is what's called K4. K for complete, I believe the German version of complete. That's why that K is there. Just K4, the complete graph. On 4 vertices. Okay. All right. Because all adjacencies are in there, that's what makes it complete. Complete means all adjacencies are made, all possible adjacencies are made. You can actually do this any way you like. You can make A1, B2, C3, D4, or just play around. Check it out. Verify that what I'm saying is not crazy. You can actually do whatever setup you like. So there's a bunch of isomorphisms between the two. Or you could say K4 is isomorphic to itself in a bunch of ways. Okay, and those are called automorphisms. When you sort of think of it in a new way, think about making this graph. How can I rearrange the vertices and still get the same graph? Those are called automorphisms. So there is a K8 that has all 8 vertices adjacent to one another. This is not K8, right? Because it's missing some adjacencies. But this one does have some automorphisms, and those automorphisms are usually referred to as symmetries. Okay. So I'll probably write that down later when we start doing some other things, but we are going to use that sort of thinking. That's pretty important. All right, so on this, so far, I've only shown you things that are isomorphic. I've not shown you failure of isomorphism yet, so that's what I need to do on the next video, and that's what we'll do. And just keep in mind, we're going to need to think much more cleverly when we need to show two things are not isomorphism, because what we have to show is not that we're bad at setting up isomorphisms, so we need to show it can't be done at all. And that can be much trickier than just setting up an isomorphism. Okay? All right, so I'll see you on the next one.